Aircraft reversers reduce landing distance by up to 30%. Because, they are very important in aircraft. Today, we will learn how they work. Don't forget to subscribe and fasten your seatbelts. In the final phase of flight, when the aircraft touches down on the runway, safe and efficient deceleration becomes a critical priority. One of the most important systems for this process is a thrust reverser, a sophisticated mechanism installed on jet engines designed to redirect exhaust flow forward, helping to reduce speed during landing. Thrust reversers are not used in flight. Their use is restricted to ground operations immediately after wheel touchdown, and their activation depends on the landing gear being fully deployed. The system is designed to work in conjunction with aerodynamic brakes and wheel brakes, giving the pilot greater control over the aircraft and helping to reduce the runway length required for a complete stop. There are three main types of thrust reversers used in commercial aviation: clamshell doors, bucket doors, and cascade-type fan reversers, the latter being the most common in modern turbofan engines. The bucket door type, often found in older turbojet engines, uses a set of metal doors hinged at the rear of the engine that close over the exhaust stream, redirecting gases forward and outward. This redirection of thrust helps slow the aircraft, but the system is relatively heavy and less efficient compared to modern alternatives. Cascade-type reversers, widely used in turbofan engines, function differently. Reverse thrust is achieved by redirecting the fan airflow, the largest volume of air moved by the engine, forward through special grills known as cascades. This redirection occurs when external panels slide open, exposing lateral outlets, while internal deflectors called blocker doors are positioned to guide the bypass airflow out through the side openings. As a result, air that would normally be expelled backward is partially directed forward and outward, generating a braking force. The system is operated by the throttle levers in the cockpit. After landing, pilots pull the lever beyond the idle detent, activating the reversers. Safety sensors ensure that the reversers can only be deployed when the aircraft's landing gear is fully extended and in contact with the ground. This safety logic prevents inadvertent in-flight deployment, which could cause loss of control and lead to serious accidents. From a technical standpoint, the actuation of thrust reversers can be hydraulic, pneumatic, or electric, depending on the aircraft design. For example, Airbus A320 family aircraft use pneumatically actuated reversers powered by engine bleed air. Boeing's 737 aircraft use hydraulic systems. More recent designs, such as the Airbus A350, use electric actuation, which reduces system weight and mechanical complexity. It's important to note that thrust reversers are not considered primary braking devices. Their main purpose is to assist with deceleration, especially on wet, short, or contaminated runways. On long, dry runways, wheel brakes alone are often sufficient to stop the aircraft, and the use of reversers may be minimized to reduce mechanical wear, noise, and fuel consumption. Thrust reverser maintenance is critical for operational safety. Regular visual and functional inspections are carried out to verify the condition of hinges, actuators, sensors, and moving panels. A malfunction in the system can result in asymmetric reverse thrust, causing the aircraft to veer off course on the runway, which requires immediate correction. In summary, thrust reversers are essential components of the braking system on jet aircraft, significantly contributing to safety and efficiency during landing. Their operation, though invisible to passengers, is a result of precise engineering and strict standards of design, operation, and maintenance. These systems represent an additional layer of protection in the complex environment of modern commercial aviation.